Okay, in this video we'll be going through the 2020 Scholarship Physics exam. Okay, question 1. A capacitor, ideal inductor, and a 12 ohm resistor are connected in series to a 6.5 volt RMS variable frequency power supply. State the conditions for resonance in a circuit of this type and describe what you would measure to determine when resonance has been reached. Okay, so we know a circuit is in resonance when XL is equal to XC. And because total impedance is equal to XL minus XC squared plus the resistance squared. If XC is equal to XL, then this cancels out. And so total impedance is equal to the square root of R squared. Thus, total impedance is equal to the resistance. And so at this point, resistance is at a minimum and therefore current will be at a maximum as V is equal to IZ. So one way we could measure this would be that the current is max, so we measure max current. But this is kind of a trashy way to answer this question, because how do we know what is max current, right? If you have no other reference point. So we can go about this a different way. Another way we can go about this is that the voltage of the inductor is equal to the current times the impedance of the inductor. And the voltage of the capacitor is equal to the current times the impedance of the capacitor. Now we know in a series circuit, current is the same all throughout. So therefore, if XL is equal to XC, and we know these currents are the same, therefore VL must equal to VC. And so one way we can measure if resonance has been reached, we can say that the voltage of the inductor is the same as voltage of the capacitor, right? That's one way we can measure this. There is another way in which we can measure if resonance has been reached, and it involves this equation here. So if V is equal to IZ, that means Z is equal to V over I. Therefore, the voltage of the supply over current, again as current is the same all throughout, we can just leave it as I, is equal to the square root of the voltage across the inductor all over I minus the voltage of the capacitor all over I, and that's squared, minus voltage of the resistor all over I, and that's squared also. Now again, as we know that the voltages across the inductor and the capacitor are equal, this again cancels out, and so we get Vs over I is equal to the square root of Vr over I squared. And so thus Vs over I is equal to Vr over I. Now, as the i's in both cases are equal, we can just get rid of them, and so Vs is equal to Vr. Therefore, another condition for resonance is that the supply voltage is equal to voltage across the resistor, and that is a second way we can measure. So we have two ways. You only need one for this question, but I've given you two. Technically three for the current one, but again, that's trash, so get rid of it. So, two ways. Okay, so if a circuit like this is at or near resonance, it is possible for both the inductor RMS voltage and the capacitor RMS voltage to exceed the RMS voltage of the power supply. Explain how this can occur. The RMS voltage is an average voltage related to the power output of the component. That's just us defining what RMS voltage actually is. The voltage of the inductor, voltage of the capacitor, and voltage of the resistor are not in phase. The voltage of the inductor leads the voltage of the resistor by 90 degrees, and the voltage of the resistor leads the voltage of the capacitor by 90 degrees. And so that is our phasor diagram, right? If we have a phasor, this is our VL, and we have that midpoint, and this is our voltage of the capacitor. And this is our voltage of the resistance. And so you can see here that VL leads VR by 90 degrees, and VR leads VC by 90 degrees as well. The voltage of the supplier is a vector of all three voltages, thus Kirchhoff's law is not violated. Sweet as. The frequency of the power supply is adjusted while the supply voltage remains constant at 6.5 voltage RMS voltage. When the frequency of the supply is 134, the current in the circuit is 0.4 amps. The supply frequency is then increased and the current changes, but at 199 Hz, the current in the circuit is again 0.4 amps RMS. None of the components are changed while this occurs. Explain how it is possible to have the same current in the circuit at two different frequencies. Okay, so we know that voltage RMS is constant. Thus, as V is equal to IZ, the only factor that will change the current is our total impedance. So we know that Z is equal to the square root of XL minus XC squared plus R squared. The only two things that determine total impedance is the difference between XC and XL and our resistance. In this case, our resistance is constant also. Therefore, the only thing that will change total impedance is the difference between XC and XL. So we know that XL is equal to WL and XC is equal to 1 over WC. So the components aren't changed during this time. So we know that the inductance and the capacitance will not change during this time. So we know that the angular frequency is the only thing that changes. So as angular frequency is equal to 2 pi f, therefore that angular frequency is directly proportional to the frequency. So if frequency increases, then angular frequency will also increase. So through this whole discussion, we can now determine that the frequency directly affects the current. Because if frequency changes, that means XL and XC will change, therefore total impedance will change, and thus our current will change. So that means we can graph this. If we have our frequency on the x-axis and our current on the y, we can draw a graph like this. Now we know that peak current is when resonance occurs, right? That's when XC is equal to XL at this point right here. And the reason why we have this shape of graph is because when frequency increases, angular frequency will increase thus. If angular frequency increases, that means XL will increase, but if angular frequency increases, then XC will decrease because these are inversely proportional. Thus at lower frequencies, like right here, our XE is going to be much greater than our XL, thus there will be a large difference between XL and XC, therefore our total impedance is going to be larger, and therefore our current is going to be smaller, as we can see here. And same thing on the other side, at this point right here, we're going to have a higher frequency, and therefore our XL is going to be much greater than our XC, and therefore again the difference between XL and XC is going to be large. That means there's a large total impedance, and therefore our current is going to be small. And then that same logic is why we get a peak at XC is equal to XL, because there is no difference between the two, thus our total impedance is minimum, and so our current is max. And so given that, now we know that the graph goes kind of like a parabola, so it goes up and then it goes down. So there is a point, let's say roughly here, and roughly here, where there is going to be 0.4 amps. And so from here, we can see that 0.4 amps occurs twice. And from our discussion, we know that this occurs when XC is greater than XL, or when XL is greater than XC. So let's write that down. Total impedance in the circuit is determined by the resistance and the difference between the capacitor reactance and the inductor reactance. Thus, as resistance is constant and voltage is constant, due to V equals IZ, 0.4 amps can be achieved when XL is greater than XC or when XC is greater than XL. Thus, 0.4 amps can be achieved twice. Calculate the values of the capacitance and the inductance in the circuit. So, as we know, V is equal to IZ, and therefore Z is equal to V over I. In this case, we know our voltage is 6.5, and we know our current, which is 0.4. So we have 6.5 divided by 0.4. And that gives us a total impedance of 16.25 ohms. There we go. So therefore, as Z is equal to the square root of our X squared plus R squared, where X is our XL minus our XC, right? That's our total reactance. We can rearrange this to find our total reactance. And so X is now equal to z squared minus r squared. And so in this case, we also know our resistance, which is as if seen above, which is 12 ohms. And so our total reactance is equal to 16.25 squared minus 12 squared. And that gives us a total reactance of 10.96 ohms. Okay, so now that we have that value, we can keep it there as it'll come in handy later. But for now, let's move on to building some separate equations. So for our first frequency, we know that that is 134 hertz, as seen up here. And so therefore, as our angular frequency is equal to 2 pi f, our angular frequency for f1, which we can label omega 1, is equal to 2 pi 134. Now to keep whole values, I'm going to call this 268 pi, and so that is 268 pi radians per second. And so in the case of our 134 hertz, this is when we have our low frequency, and so we can gather that our XE is going to be greater than our XL. And so as our XC is greater than our XL, we can say that 1 over our omega C minus our omega L is going to equal to our total impedance. This would work the other way around, except you would get a negative total reactance value, which would still work because at the end of the day, our total reactance is just the difference between XC and XL. It doesn't actually matter which way you do it. But to keep positive values, I have done it this way. So we do the larger value minus the smaller value, which in this case, as we discussed previously, XE is greater than XL at 134 hertz, so that's why I have done it this way. And in both of these cases, these are going to be angular frequency 1, which we have labeled up here. Okay, so now we can rearrange for our inductance. So we can go that 1 over omega 1 C minus X is equal to our omega 1 L. So dividing both sides by omega 1, we get 1 over omega 1 squared C minus X over omega 1. And that's equal to our inductance. So this is our first equation. So for our second frequency, we know that is 199 hertz, as seen over here. And so again, our angular frequency, which we'll label omega 2, for our second frequency is 2 pi 199. And that's equal to 398 pi radians per second. Again, for value's sake, just leaving it as that. And so at this point, this is our high frequency, and so this is at this side, and therefore our XL is greater than our XC. Therefore, we can form the equation omega 2L minus 1 over omega 2C is equal to our total reactance. Again, rearranging for L, we get omega 2L is equal to X plus 1 over omega 2C. Dividing both sides by omega 2, we get L is equal to X over omega 2 plus 1 over omega 2 squared. That's a bit trippy, and then times by C. And now this is our second equation. So now, as both equation 1 and equation 2 both equal our inductance, we can make them equal to each other. So therefore, 1 over omega 1 squared C minus X over omega 1 is equal to our X over omega 2 plus 1 over omega 2 squared C. Now, for this, we are going to solve for our capacitance. And so to do that, we need to gather our like terms. So I'm going to move this over here and move this over here. So we get 1 over omega 1 squared C minus 1 over omega 2 squared C is equal to our X over omega 2 plus our X over omega 1. Now we can times both sides by our capacitance to get 1 over omega 1 squared minus 1 over omega 2 squared is equal to our X over omega 2 plus x over omega 1, and this is all multiplied by our c. And so we can divide both sides by this right here, and we get 1 over omega 1 squared minus 1 over omega 2 squared, and that is all divided by our x over omega 2 plus x over omega 1, and that is all equal to c. And so we know our omega 1 and omega 2, which is just 268 pi and 398 pi. We also know our total reactance value, which we calculated earlier, which is 10.96. So plugging in our values, we get 1 over 268 pi squared minus 1 over 398 pi squared, and that's all over 10.96 divided by 398 pi minus 10.96 divided by 268 pi. And that's equal to 3.54 times 10 to the negative 5 farads. There we go. That is our capacitance. So we have ticked one of the calculations. Now we need to calculate the inductance. So now to find the inductance, we can choose either this equation here or this equation here, as we have our omegas and we have our capacitance now. So now we can just solve for our L. So let's pick this equation here. So we have 1 over our omega 1c minus our omega 1L. That's all equal to our total reactance. So plugging in our numbers, that's 1 over 268 pi times by our capacitance, which we just found, which is 3.54 times 10 to the negative 5. And that's all minus our omega 1 again, which is 268 pi, and that's multiplied by our inductance, which is what we're trying to find, and that's all equal to our 10.96. So now solving for L, we can get 1 over 268 pi again. Now we can divide by our 2689. So now that we got our inductance on the right hand side, we can divide by our 268 pi on both sides to get L by itself. And that's all equal to our inductance right there. And chucking that in our calculator, we get 0.0268 henries as our inductance. Okay, question 2. For a moving source of sound, the frequency heard by a stationary observer can be calculated using the following equation. Explain the use of the plus and minus symbol in the equation. Okay, so if there is a plus symbol used, this means that the source is moving away from the observer, but if there's a minus used, that means the source is moving towards the observer. Now, this makes sense because we know that, because if the source is moving towards an observer, so let's say like this, we have a source, and we have a little observer here. So if the source is moving this way, that means it's catching up to previously emitted wavefronts. So we know that the wavefronts behind it is going to be spaced out, and the wavefronts in front is going to be bunched up, as seen there. And so, due to V equals F lambda, if the perceived wavelength is decreased, this means as the speed of the wave is the same, and therefore as the velocity of the wave remains constant, therefore the observed frequency is going to increase. Therefore, in this case, as the source is moving towards the observer, in our paragraph up here, we have defined that as when the source is moving towards the observer, we use a minus. So in this equation, if we chuck a minus in there, that the denominator is going to be a smaller value, right? Thus, the observed frequency must increase, mathematically speaking, based on this equation. And that's what we see in our theory. Same thing in reverse. Let's say our dude is going to be over here now. The source is moving away, so the perceived wavelength is going to increase, and therefore the frequency is going to decrease again as the speed of the wave is constant. Therefore, we now chuck a plus up there, and so now the denominator is now going to increase, and so now the perceived frequency must decrease. which is, again, what we see with our theory, right? Okay, and there we go. State the assumptions made about the velocity of the moving source of sound. The two assumptions is that the velocity of the wave is constant and directly towards the observer. So when we mean directly towards the observer, as in the source is approaching directly towards the observer, and if the source were to keep going, it will go directly through the observer. So we can write that in. Okay, so the velocity of the source is constant, and the velocity of the source of sound is directly towards the observer. An object is moving in a circle with a radius of r at a constant speed of vs while emitting a sound at a constant frequency. At the instant the observer at point P hears the sound at a maximum frequency, the source has reached the position indicated on the diagram. Show that theta is equal to this heinous equation here. So first things first, we can split this theta up into two parts, like so. And we can call this part alpha, and we can call this part phi. And we can also draw a line directly to point P, which creates a right angle at this point right here, and let's call this distance x. So as you can see, this line is the entire radius of the circle, so that line is also r. So that's r, but that is also r. So we can redraw this triangle somewhere else so it's easier to work on, right? Kind of goes like this, and like this. And that's our right angle, that's our distance r, that's our x, and that's our d. So as you can see, this angle here, right here, is this angle here, and as we have labeled this angle phi, this angle must be 90 minus phi. So we can put that in here, that's 90 minus phi. Therefore, as all angles in a triangle has to equal 180 degrees, as this is 90 minus phi, this therefore has to equal phi, right? So that's that angle there, that's phi right there. So using our trig, we can say that phi is equal to the inverse sine of r over d, right? We have our opposite and we have our hypotenuse, as this is opposite from the right angle. And that looks suspiciously familiar. So that is our phi right there. So as indicated, this whole angle right here is theta, and we've found 1/2, which is phi. So our theta is equal to our alpha plus our phi. We have found phi, so we've found half of our theta. Now we need to find our alpha, which we know is this part here because we've already found this part. So let's first start off with this bit right here. That bit right there, that is our distance x. Using our Pythagoras, we get a squared plus b squared is equal to c squared. In this case, our d is our c, and these can be our a and our b. So therefore, applying it to this situation here, we get r squared plus x squared is equal to d squared, and therefore x is equal to the square root of d squared minus r squared, which is what we get here. So therefore, that is x. Okay, good to know. So what is the distance x? Like, what is that? Well, if we look at our diagram, we see our Vs, our source is roughly there, right? This distance x is where the source was when the sound was emitted, right? We know that in Doppler, when we have a source and it's moving, it catches up to previously emitted wavefronts, right? And so therefore, when the source emitted the sound that the observer at point P heard, it emitted it back here. But now the source is down here. So distance x is the distance between the source and the observer when the wavelength was emitted by the source that the observer is currently hearing. So given that, we need to account for the distance traveled by the source in this time, right? That's the distance that the source travels during that time. So distance, in terms of circular motion, we currently use as theta, right? And theta is equal to omega t, right? But in this case, we don't use theta, we're actually going to use alpha because alpha is the angle that we have defined. So alpha is equal to omega t. Now our omega is equal to our velocity over our radius, where in this case our velocity is the velocity of the source, and that's all over our radius r, which we have here, which is also here. So that's our omega. However, for our time, we can use our trusty velocity is equal to distance over time, where our time is our distance over our velocity. Now the distance traveled, that's this distance x, so we can say the square root of d squared minus r squared, and that's all over the velocity of the wave, because this time is a time taken for the wave to reach point P, so the distance traveled by that wave is our x, which is this, and it's going at the velocity of the sound wave, right? So VW. And so subbing that in, we can get alpha is equal to Vs over R times the square root of d squared minus r squared all over VW. And that looks like Vs d squared minus r squared all over VWR, which if you looks like that. And so finally we can get our theta is equal to our Vs square root d squared minus r squared all over VWR plus the inverse sine of r over d. There we go, that is our final equation. Sweet as. The Doppler effect can also be observed when a moving observer approaches a stationary wave source at speed v0. The relationship of the apparent frequency when an observer moving at speed v0 approaches a stationary source, given by that equation there. Explain when the observer would experience the greater Doppler shift, when the source approaches a stationary observer or when the observer approaches a stationary source at the same speed. So if we imagine our Doppler scenario, when we have a source moving, let's just for this example use a moving source. The faster the source moves, you can imagine the smaller the apparent wavefronts, right? So this is a fast, so a high velocity. Whereas if we have a low velocity, this is going to look like something like this, right? I'm trying to make these bigger than these, which I think I've done a pretty good job of. So the observed wavelength is going to be smaller for the high velocity than the low velocity, right? Because that makes sense. Because the higher the velocity, the faster the source catches up to its previously emitted wavefronts. Okay, that makes sense. So we can imagine that the greatest Doppler shift is going to happen when the velocity of the source is equal to the velocity of the wave. So for this question, in order to mathematically debunk which one will be greater using the equations, we can say that the velocity, which is v, which is what they're given us, is equal to velocity of the wave. So speed of sound in this case. Or if we were using light, then it would be the speed of light, right? Speed of, it will be c. So for our stationary source, we can say that f prime is equal to our f VW plus V0 all over VW. Now our V0 in this case will be our V. And so as V is equal to VW, we can say that F prime is equal to the frequency times VW plus VW. And that's all over our VW. And so expanding this out, we get F prime is equal to 2F VW all over VW. And so this cancels out with this. And we get the observed frequency is double the frequency of the source. So that is the max frequency we're going to get, right? As discussed previously, the greatest Doppler shift is going to be when the speed of whatever is moving. So in this case, the observer is moving. So when the observer is moving at the speed of the wave, the highest Doppler shift you're going to get is double the frequency of the source. However, if we use a regular Doppler scenario where we have a moving source, we get F times VW all over VW minus Vs, right? Because when a source approaches a stationary observer, so we're on approach right now, so that's why we do a minus. And so as we know that the velocity of the source in this case is going to be our V equals VW. So we get F is equal to F times VW all over VW minus VW. So we get F prime is equal to F times VW all over 0. Now, since we're dividing by 0, our observed frequency is going to be approaching infinity. That's trash. Okay, how do we draw our infinity symbol? Okay. That's not good. Okay, that's good. That's good. Okay. So our observed frequency is going to be approaching infinity. I should put that right there. Approaching. So now that we're done the maths, we can write some comments on this. So first I'll write a comment on when we have a moving observer. If an observer moves towards the source at VW, the effective wave speed is doubled. And what I mean by effective wave speed doubled is if we have our source emitting a wave at VW and we have an observer, little Timmy here, right? Let's call this guy Timmy, right? And Timmy is moving at VW. Therefore, the relative speed at which the speed of the wave is moving towards Timmy is going to be 2VW. Therefore, the effective wave speed is doubled. While the wavelength remains the same, thus due to V equals F lambda, the frequency will have to double. Alright, so now writing comments about our moving source and our stationary observer. So if the source moves at the wave speed, each subsequent wavefront is emitted on top of the previous wavefront. So what we mean by that is that we have our situation where we have our moving source. And previously, when we have a source not moving at the speed of sound or the speed of the wave, we would have our wavefronts like this, where our wavefront in front of the source is going to be smaller than the wavefront behind the source. And that's again because the source catches up to its previously emitted wavefront. But if the source is moving at the speed of sound or the speed of the wave, each wavefront is just going to be on top of each other, like this, right? Just constantly on top of each other. And so lambda is effectively just 0 at that point, right? So thus the wavelength is effectively 0, thus the perceived frequency is going to be infinity due to V equals F lambda as VW is constant, right? So V equals F lambda, right? So frequency is equal to the velocity of the wave divided by its wavelength. So if F is equal to the velocity of the wave divided by lambda, which is 0, the frequency is going to be effectively infinity, which is what we derived here using our Doppler equation. And so drawing a conclusion on both scenarios, so for the same relative speed, the stationary observer with an approaching source will have the greater Doppler shift than the moving observer with the stationary source. Okay, sweet as. Okay, question 3, collisions. A slider S1 is moving along an air track at a constant velocity of v. It collides elastically with the stationary and identical slider S2 as shown in the diagram below. Explain why S1 stops and S2 moves off with the velocity v. Okay, so this is a simple kinetic energy and momentum conservation question, so we can get right into that. So first off, starting with our EK, we can get our half mv squared, where in this case v is the velocity of s1 before the collision, and we get after the collision, which is our half mv squared 1. So our v1 squared is the velocity of our s1 plus our half mv2 squared, where our v2 is the velocity of our s2. Now, because these are identical sliders, our masses are going to be the same, and so we can take out our half m on both sides. v1 squared plus our v2 squared. So we can cancel these out, and so we get our v squared is equal to v1 squared plus our v2 squared. Okay, that's our first equation. Now, using our conservation of momentum, we can do the same thing where our v is the velocity of s1 before the collision, and we get our mv1, which is the velocity of s1 after the collision, plus our mv2, which is the velocity of s2 after the collision. Again, we can take out our masses as they are both identical on both cases. So we get mv is equal to mv1 plus v2. So we can cancel out our m's, and we get v is equal to v1 plus v2. Now we can sub this into here, and we get v1 plus v2 squared is equal to v1 squared plus v2 squared. Therefore, in order for this to be true, our v1 has to equal 1, and our v2 has to equal 0, or our v1 is equal to 0, and our v2 is equal to 1. So we need to decide which scenario is true. So analyzing the situation, we have S1 hitting S2, and S2 experiences the unbalanced force in this case. Therefore, S2 must move off with the velocity, and so this second scenario is the true solution. So we can write that down. As S1 experiences an unbalanced force, it must have the velocity. Thus, V1 is equal to 0 and V2 is equal to 1. Thus, S1 stops and S2 moves off with a velocity V. In a second experiment, S1 is given a velocity of 1 meters per second along the air track and collides elastically with another slider S3 that has a mass of m times that of S1 and is also stationary. Show that after the collision, the velocity of S1 is given by this equation here, and the velocity of S3 is given by this equation here. So, same thing as before, we're going to approach this equation using the conservation of kinetic energy and the conservation of momentum. So let's start with our conservation of kinetic energy. So we again have our half mv squared, which again, as S1 is the only thing moving, this is going to be the kinetic energy of S1. And so after the collision, it's going to equal to half mv1 squared, which is now the kinetic energy of S1. And after the collision, there's also going to be the kinetic energy of S3, which is going to be n mv3 squared. Now, the reason why we add that n is because we have this condition here where the mass of S3 is n times that of S1. So if the mass of S1 is considered m in both of these cases, then nm must be the mass of S3. So again, we can take out our half m on both sides and we get half mv squared is equal to half m times v1 squared plus nv3 squared. So we can cancel these out and we get v squared is equal to v1 squared plus nv3 squared. Okay, now that we have this equation here, we can leave it there. And let's go on to our momentum. We get the momentum before the collision, and that's equal to the momentum after the collision, which is going to be mv1 plus nmv3. And so we can take out our masses again, and we get mv is equal to mv1 plus nv3. Cancelling out our masses, and we get v is equal to v1 plus nv3. Now we can rearrange for our v3 and we get v minus v1 over n is equal to our v3. Now the slider S1 before the collision is given a velocity of 1 meters per second. So we can plug that in where we have our 1 squared is equal to our v1 squared plus nv3 squared. Now 1 squared is just 1, so we can simplify that down to just 1. And same thing over here. This is the velocity before the collision, so we get 1 minus v1 over n is equal to our v3. Now that we have an equation for v3, we can sub this into here, and we get 1 is equal to v1 squared plus n1 minus v1 over n squared. And we can rewrite this as 1 is equal to v1 squared plus n 1 minus v1 over n, and then 1 minus v1 over n, like this. And now expanding this out, we get 1 is equal to v1 squared plus n v1 squared minus 2v1 plus 1, all over n squared. Now we can cancel out that power, and we get 1 is equal to v1 squared plus v1 squared minus 2v1 plus 1 all over our n. And we can times by n on both sides, and we get n is equal to nv1 squared plus v1 squared minus 2v1 plus 1. Now we can gather our like terms, and we get n is equal to v1 squared n plus 1 minus 2v1 plus 1. Making this equation equal 0, we get 0 is equal to v1 squared n plus 1 minus 2v1 plus 1 minus n. Now, as you might be able to see, this is a quadratic. And so to solve this, we can use our quadratic formula that we should be familiar with from calculus. So we have x is equal to negative b plus or minus the square root of b squared minus 4ac all over our 2a. And so this n plus 1 is our a, this 2 right here is our b, and this 1 minus n is our c value. And so we can plug that in, where our x in this case is going to be our v1. So we have v1. So we have our negative b, which in this case is negative 2. So negative times negative 2 is just going to be positive 2. And we have our plus or minus negative 2 squared minus 4 n plus 1 minus n. And that's all over 2n plus 1. Simplifying this slightly further, we get 2 plus or minus 4 minus 4, 1 minus n squared, all over our 2n plus 2. Continuing with the simplification, we get v1 is equal to 2 plus or minus the square root of 4 minus 4 plus 4n squared, all over 2n plus 2. And so v1 is equal to 2 plus or minus 2 minus 2 plus 2n, all over 2n plus 2. And so v1 is equal to 2 plus or minus 2n, all over 2n plus 2. And so this can be simplified to v1 is equal to 1 plus or minus n, all over 1 plus n. And so if this is a plus, then we get v1 is equal to 1 plus n, all over 1 plus n, which is equal to 1. Or we get a minus, and n minus n is equal to 1 plus n, and that's equal to v1. And so what you'll see if we go back up, we need to show that v1 is equal to this equation here, which is what we have found. There we go. So that is our first equation found. Okay, so now that we have v1, we can find an equation for v3, which we have up here, and we can sub that in. So our v3 is equal to our 1 minus v1 all over n, and so v3 is equal to 1 minus our 1 minus n over 1 plus n, and that's all over our n. Now to simplify this further, we can times the top and bottom by 1 plus n, and we get 1 plus n minus 1 minus n all over n 1 plus n. And that gives us 2n all over n 1 plus n. These n's cancel out, and we get v3 is equal to 2 over 1 plus n. And as you will see, this is the second equation that we're trying to find. Okay, so quite a long process, but we got there in the end. Okay, in a third experiment, the two sliders change roles so that S3 is now moving at velocity of 1 meters per second along the air track and collides elastically with S1, which is initially stationary. Use the answers from our previous question, and noting that S1 has a mass of 1 over n times that of S3. Showed that after the collision, V3 has that velocity there, and V1 has that velocity there. Okay, so this question is actually a lot more simple than it may seem. What we're literally doing is, as it says, we're just switching the roles. So previously, as you might remember, we did our kinetic energy and momentum conservation equations. And in these equations, we multiplied the mass of S3 by n times, because it's said up here. So for this, as S1 and S3 have swapped places now, we can essentially just replace n with 1 over n in all these equations, and we'll get the answer. So the equations that we had was that V3 is equal to 2 over 1 plus n, and that V1 is equal to 1 minus n over 1 plus n. So let's replace our n with 1 over n in all scenarios, and we get V3 is equal to 2 over 1 plus 1 over n, and we get V1 is equal to 1 minus 1 over n over 1 plus 1 over n. And now we can times this whole thing by n, and we get V3 is equal to 2n all over n plus 1. And we can do the same thing for V1, times this whole thing by n, and we get V1 is equal to n minus 1 all over n. Now that V1 and V3 have swapped positions, we actually have to swap these labels. And now that V1 is actually now the equation that is 2n over n plus 1, and V3 is now n minus 1 over n plus 1. And as you can see, V3 is now equal to this, and V1 is now equal to this. So a lot simpler than it may first look. So use the result in the previous question to show that if a massive bat is swung at a top speed of v to hit a stationary light ball in an elastic collision, the top speed of the ball is approximately 2v. So it tells us to use the result of the previous question, so we can analyze the previous question to see what it means. And we can see that in this case we have S3 which hits S1, and so if we take that idea and apply it to this question here, we can say that the ball actually takes the place of S1 in this case, because S1 is the thing that gets hit and S3 is the thing that hits S1. So the bat is now taking the place of S3 and the ball takes the place of S1. So we want the velocity of S1, which is this equation here. So this is going to be the velocity of the ball, which is equal to 2n over n plus 1. Now, as the massive bat is swung at a top speed of v, all velocities before and after are going to be scaled up by a factor of v, so we can scale up this equation by a factor of v by going 2nv all over n plus 1. So now looking at this equation, remember our n is actually the factor that the mass of S3 is multiplied by. And so the key idea here is that we have a massive bat and a light ball. So a massive bat meaning that the mass of the bat is like large, right? For large n values, right? If we have a very large n value, that means this plus 1 is going to be insignificant, right? And so we can kind of just omit it from the equation, and we get v1 is equal to 2nv all over n. These n's cancel out, and we get v1 is equal to 2v, which is what we're trying to find. Okay. In the reactor of nuclear power stations, the fast neutrons with energies of about 2 megaelectronvolts are typically produced by fission of uranium. For a chain reaction to occur, these neutrons must be slowed down to energies of 1 electron volt or less by colliding with materials such as heavy water, which is just water which contains a hydrogen nuclei with an addition neutron. Calculate the velocity loss when these fast neutrons are slowed down. So this question, again, very straightforward. All we're doing is just calculating the velocity of the neutron when it has 2 megaelectron volts of kinetic energy, and the velocity when it only has 1 electron volt of kinetic energy. And we just subtract the two to see the loss, right? So when it has 2 mega electron volts, so first off, what we need to do is convert electron volts to joules. And so the way we do that is by timesing by the charge of an electron. And so we get our EK is equal to 2 times 10 to the 6, because mega, which is this big N, is times 10 to the 6, which is 6 zeros essentially, so millions. So 2 million electron volts. And that's times by 1 point, what's the charge of electron? What's given? 1.602, okay. That's why it's important to check what the values are given, because usually it's just 1.6 and you'll forget that 02 and you'll get the question wrong. So that's why it's important to check. And that gives us a kinetic energy value in joules of 3.204 times 10 to the negative 13 joules. Okay, so now we know our EK is equal to our half mv squared, and so our velocity is equal to the square root of 2ek all over its mass. So we can plug in these numbers, and we get the velocity of the neutron is equal to 2 times 3.204 times 10 to the negative 13 all over the mass of a neutron, which is 1.675 times 10 to the negative 27. 1.675 times 10 to the negative 27. And that gives us a velocity of 1955942 meters per second. Okay, so that is the velocity of the neutrons when they have 2 megaelectron volts of kinetic energy. So now what about when there's only 1 electron volt? So we do the same process where we convert our EK into joules. So that's just 1 times 1.602 times 10 to the negative 19, as you might be able to guess without a calculator, that's just 1.602 times 10 to the negative 19 joules. Okay, so now we got our velocity equation, which is 2ek all over its mass. So v is equal to the square root of 2 times 1.602 times 10 to the negative 19 all over 1.675 times 10 to the negative 27. And that gives us a velocity of 13831 meters per second. Okay, now to see how much the velocity has been slowed down by, we do this minus this. So we get 19559342 minus 13831. And that gives us a velocity of 1954593 meters per second. There we go. Using the results from parts A and B, explain why heavy water is used to slow down fast neutrons, and suggest a reason why heavy water is used rather than common water. So first, let's look at part A. When we look at part A, when the masses of S1 and S2 are the same, what we actually get is the velocity equals 0. Right? So the velocity goes right down to 0. However, in part B, where is part B? In part B, we have a massive mat and a very light ball, and so what we get is actually just double the velocity, which is not what we want. We want to slow down that neutron, remember? What we can say is when the masses of the neutron and whatever material it is colliding with are similar, that is when we're going to get the most slowdown of the velocity. So we can write that in. So as we just discussed, when the masses are the same, this is when the greatest velocity reduction takes place. Okay, so why is water used in general? Let's not worry about the heavy water right now. Why is water used? So we want to slow down neutrons, and we want something that has a similar mass to neutrons. So water, which is H2O, is made out of hydrogen atoms. So now specifically looking at the hydrogen atom. So a hydrogen atom is just a proton and an electron. Right? And protons and neutrons actually have very, very similar masses. And so as the electron has a mass that is way less than that of a neutron and a proton, we can effectively just ignore the electron in terms of mass. And so a hydrogen atom is effectively the same mass as a neutron. Now, same mass should be put in quotation marks. They're actually similar. In reality, they're not quite the same. But what we want is something that's very, very close, right? Because as we saw, if they are the same mass, that's when we get it goes down straight to 0. But we want something that's similar in mass. And so the hydrogen in water fulfills this role very, very well. And so we can put that in words. So the hydrogen atom in water fulfills this role the best, as it is effectively just the mass of a proton. Thus, the mass of the hydrogen atom and the mass of a neutron are very similar, therefore allowing for the most velocity reduction. Thus, water is the best candidate for this role. So now let's discuss why heavy water is used rather than just regular water, right? So as seen previously, heavy water is just a hydrogen nuclei that has an additional neutron. And the reason for this is because when neutrons collide with a hydrogen atom, that neutron is going to be absorbed by the hydrogen atom, thus producing what's called a deuteron. And so what that looks like is we have our proton and we have our neutron being absorbed together, and that's deuteron right there. And so deuteron is just heavy water, and so that's why regular water isn't very good, because when a neutron collides, the neutron just gets absorbed by the hydrogen atom, which is not what we don't want. We want it to not be absorbed, really. Heavy water, which is water with deuteron nuclei, is a good candidate because the neutron has already been absorbed and so is less likely to absorb another neutron. And so we can write that in. However, as the hydrogen is likely to absorb a neutron to become deuteron, thus heavy water is used as deuteron is less likely to absorb another nuclei compared to a regular hydrogen nuclei. Okay, question 4, sliding wires. A parallel pair of fixed horizontal conducting tracks, TA and TB, lie in a uniform magnetic field B, as shown. Track A is divided by a switch on either side of which rest 2 identical metal wires, each with a resistance R, that can slide without friction along the track. Okay. Initially, both wires W1 and W2 are stationary. With the switch open, wire 2 is given a short push, to the right and then moves at a constant velocity v. Explain what occurs to the electrons in W2 as they move through the magnetic field. So for this question, we will need to use our right hand rule. So if we point our index finger into the page and our thumb to the right, which is the direction that the wire is moving, so to the right, and we see we have an upwards force. Now the important thing to know is that that upwards force is for positive charge, not negative charge. And so if we have an upwards force for positive charge, when our electrons are going to have a downwards force, right? Opposite. Another way you could look at this is just use your other hand. So if you put your index finger into the page, thumb to the right, then our middle finger goes downwards, and that is the force experienced by the electrons. And so we can write that in. The electrons will experience a downwards force. Explain why W2 slides along at a constant velocity. So a key idea here is that both sliders can slide without friction along the track, and therefore the only force that is experienced on W2 is a downwards force, which we just discussed in the previous question. But this force is at right angles to its motion, right? And so it would have no effect on W2's velocity. And so we can write that in. So because no forces act in the direction of W2's velocity, as there is no friction and the force experienced by the electrons is perpendicular to W2's velocity. Thus, due to Newton's first law, W2 will move at a constant velocity. While W2 is moving to the right, the switch is shut. Describe and explain the subsequent motions of both W1 and W2. For this, we'll go back up to the diagram to see what's happening. So when the switch is shut, so this becomes a closed path. So what's going to happen is, because of the motion of W2, there is going to be a current produced in this direction. So that's anti-clockwise, right? So now, as you can see, there is a downwards current being produced in W1. Okay, so if we use our right hand rule and we put our thumb in the direction of our current, our fingers into the field, we can see there's a force being applied to the right for W1. So W1 will now accelerate to the right. But now we use our right hand rule again on W1, and we see that we have a force being applied to the right. Our finger goes into the page again, and now we have a current being produced again in this direction, now opposing the current produced by W2. And so because of this, W2 is going to lose energy and decelerate, while W1 continues to accelerate. So you can imagine there is a point in which both W1 and W2 are at the exact same velocity, right? Because W2 is slowing down, W1 is speeding up, and so there's a point where the velocities are the same. At this point, both the currents produced by W2 and the current produced by W1 are going to be equal, and thus there is no more forces being applied on W1 and W2. Therefore, due to Newton's first law, as there's no more forces being applied on both wires, they will continue to move at a constant speed, and that constant speed is going to be the same for both W1 and W2. So let's write that down. When the switch is closed, W2's motion will cause an anti-clockwise current to be produced. This current flows through W1, thus W1 experiences a force which causes it to accelerate to the right. Due to the motion of W1, this will result in a clockwise current to be produced, which will oppose the anti-clockwise current produced by W2's motion. Thus, W2 will lose energy and slow down, while W1 accelerates. Therefore, there will come a point where the velocity of W1 and W2 are equal. This velocity is half the original velocity of W2 due to the conservation of momentum. Thus, at this point, the two opposing currents cancel out. Therefore, there is no forces acting on W1 and W2. Thus, due to Newton's first law, both W1 and W2 will continue to move at a constant and equal velocity. Determine the final velocities of W1 and W2. Explain your reasoning. Okay, so I hinted at this in the previous question, that the velocities of W1 and W2 is going to be half the original velocity of W2 due to conservation of momentum. So due to conservation of momentum is conserved. So that means the momentum initially has to equal to momentum finally, right? Therefore, as momentum is equal to mass times velocity, as mass has 2x, has doubled, thus velocity must half. And we can see that mathematically speaking if you want. We have our mv, this is the mass of w2, and this is the velocity of w2 before. And then we have the mass of w1, and that, let's say that goes at v0, plus the mass of w2, and that also goes at v0. Now the reason why we don't label the masses in this case is because both w1 and w2 have the same mass, and then we also have the same v0 because we know based on the previous questions, they both move off at the same constant velocity. And so you can see, simplifying this, we have mv is equal to 2mv0. These masses cancel out, and so the velocity is equal to 2v0. And so our new v0, which is our new velocity, is half the original velocity. And so we can make a little comment on that. The new velocity is half the old velocity. Explain the energy changes that follow as a result of the switch being closed. And so when we mean energy, in this case, we're specifically talking about EK. And so we know that our EK is equal to our half mv squared. So based on the previous question, we know that our velocity has been cut in half. And so as velocity is squared, then our EK has dropped by a quarter due to velocity, right? But we also know that our EK has increased by 2x due to mass doubled, right? Because now EK both incorporates W1 and W2, our mass is doubled, and so we have a 1/4 drop times by a 2 increase, and so that's 2/4. Therefore, our EK has reduced by a half. So, and this energy is being lost to heat in the wires due to resistance. And so you can write that in if you want as well. Okay, we're done.